Our new abstract data type of the day is the so-called priority queue, which you've seen in section, but we'll now go over this again. So the priority queue has primarily, it has only these 4 methods, and it has this add method where you can throw stuff into the priority queue. It's a bag, right? You throw stuff in it. And unlike a normal collection, it doesn't have the ability to let you check if something exists or get the nth item. Instead, it supports these funny operations, get smallest and remove smallest. So get smallest will actually go in there and find the smallest thing for you and give it to you without removing it. And remove smallest, well, it does the same thing, except it also deletes it from the priority queue. Yep. And this right here, we of course have a size method, which will be handy for various utility purposes, but that's it. That's all you get with the priority queue. So it's a really restrictive interface. But if we restrict ourselves to only having these operations, we'll see we can make something that's actually quite fast. Okay. Now I'll note here that this implementation of, or this priority queue specification here is pseudo Java, right? There's no way in this code that, notice that nothing's extending comparable or anything similar like that. So, it's kind of a little bit of a fib because Java isn't going to magically know which item is smallest, and we'll talk about that a lot later in this lecture. But for now, the minimum-oriented priority queue has this basic functionality. So what good is this thing? Well, it's good if you want to keep track of the smallest, largest, best, etc. item seen so far. And so as an example, let's consider a goal where we are, I don't know, some spy agency, and we have some kind of tapping device that's able to collect information about transactions going over wires. Okay? So we want to write a program transaction analyzer that's able to take a stream of transactions and is going to record the m highest value transactions into some kind of list. Okay? So the naive approach would be, okay, well, I was going to listen for 2 months. Okay? Now, still beeping. Serious. All right. So I hope that beep was audible so you didn't just think I was a crazy person. But yeah, there was a beep. Anyway, but you listen and you collect a list of all the items that you heard over the course of a year, then sort it, and then keep only the biggest M items. But that's very wasteful of memory. We don't really need to keep every single transaction that ever was. Instead, we can just monitor and keep only the best ones. And so we're going to give ourselves some constraints that we're only allowed to use M memory, that is big theta M memory, and the runtime should still be fast. So let's try and use a priority queue for that purpose. So what I've got here is we're going to write some code where we go through a transaction stream and somehow record a list of the highest transactions. Okay? So what I'm going to do is I'm going to make a min p queue of transactions. Then I'm going to call the top transactions, let's say. I'm going to pause for a moment so I can swap keyboards. So now we want to instantiate one of these things, though we can't do that because it is a interface. So we use a particular implementation known as a heap min pq, and by the magic of implementation inheritance and the way containers work in Java, that works, right? Just as we've done before with lists. And we'll talk about what a heap min pq is in detail in a little bit. Okay, so now we have a priority queue, and now we want to use it to record transactions, but only the largest ones. Okay. Now it might seem strange that I'm using a minimum-oriented priority queue to somehow collect the largest things, but it'll all make sense in a moment. You can do this with a max PQ, but it's actually better and easier with a min PQ. Okay, so what I'm going to do is I'm going to iterate over my transaction stream, and we're going to assume that this is something we can do, and we'll just watch transactions until there are no more that we can observe. Okay. Now what's important is we're not actually keeping a list of all these transactions. They're just flying by us, right? We're just watching them go by the window, and whenever we see one, we are going to, well, I'm going to grab it, and I'm going to add it to my priority queue. Top transactions. And so at that point, I've now taken the transaction out of midair, thrown it in my bag, but I only want to keep the largest transaction. So maybe consider how you might, what you might do next, okay? The goal is, remember that we need to use no more than M memory. We shouldn't keep all the transactions. So we need to make sure we're only using M memory. Okay, so those are always my maybe pause and think about it moments when I do that shifty look. So what I'm going to do is I'm going to say, if it so happens that if the size of my top transactions is greater than M, right? I'm starting to use too much memory. Well, what I'm going to do is I'm going to remove the smallest item. Okay, so if I ever have too much stuff in my bag, I'm grabbing these transactions out of midair, throwing them in a bag. But once I get up to m, I'm going to throw away the smallest because I'm only ultimately going to keep the m largest. Okay. And so in this way, actually, this very simple piece of code, whenever it's done, this top transactions priority queue contains the m largest things. It's a really beautiful, clever idea. Okay. So what I'm going to do next is I'm supposed to return a list, and so I need to now convert this priority queue into a list. And so what my approach will be, I'm going to say list transaction, we'll call this thing the return list, equals new array list transaction, and then I am going to say while top transactions dot size is greater than 0, I'm going to take my return list and I'm going to add the top transactions dot remove smallest, and then finally I'll return my return list, and that's it. Okay. So that is a piece of code that, given a stream of transactions, we can record the m largest, and we can do it without using a ton of memory, and as long as the heap min pq is fast, this should be pretty fast. All right. Okay, so here's our code again, now on a slide, maybe slightly different. And so the things we note here are we can track top m transactions using only m memory, and again, the API, the interface we have for our minpq also makes the code very simple. We don't have to do explicit comparisons or sort or any of that. So why is this thing called a priority queue? Well, because each item has in effect a priority, a certain value that tracks how good it is. And what I'll note is that these priorities may not be unique, right? We may have multiple transactions that are both $2,000. So those two transactions should have the same priority. And that'll be important on this next slide when we talk about implementations. So how would we implement a priority queue? There's a bunch of possibilities, and in class I'll have people shout out some examples, but right here I'll just make some up. So let's suppose we go with an ordered array. That's one way we could try to implement this data structure. So adding to an ordered array. What is the worst case runtime? Well, it's n. You have to, if you insert something into an ordered array and it happens to be the new smallest item, then I have to shift everything over in the array. How about get smallest? Well, that should be pretty fast. Just grab the front item. And remove smallest? Well, I have an ordered array, so if it's removing the front one, then I have to shift everything over the other way. Or I have to shift everything back. Could you do a little better? Maybe leave some kind of dead space at the front? Maybe. But yeah, so you might be able to do a little better than this, but you're not going to do better than this right here. Okay? So a little bit of implementation details as to whether this is n or something else, but the most naive solution is n. Okay? But an ordered array is just not going to cut it because we're going to have to shift things around no matter what. Okay. What's a data structure we've created that allows us to keep items in order that's very fast? Okay. What about a bushy BST? So bushy BST. You add something to the BST. You just throw the transaction in there, and if they're sorted based on the order of the transactions, then that should be quite fast. We find our place in the tree and live there. Get the smallest. Okay, so I have a big bushy BST, and I want to get the smallest thing in it. How do I do that? Well, that's a problem we haven't considered before, but something I do expect you guys to be able to figure out. But basically, you just go left until there's nothing else, and that should be log in, as long as it's bushy. And then finally, remove smallest will be log in. And so you can play some tricks, like keeping a pointer to the smallest thing always, so you could make this constant time instead, but login's good enough. So there's some issues, though, with the bushy BST. While this is very fast, and we should be perfectly happy with it, we're not going to do any better, there are some issues, which is maintaining bushiness is annoying. But more importantly, that last thing I was saying about transactions with the same value, why would that be an issue? Think about that for a moment. So I have a bunch of transactions, multiple with $2,000 values. Okay, well, the issue is that in a BST, we don't allow duplicates. So handling duplicate priorities is awkward. Now, it's possible, because what you can do is use the BST as a way to map from transactions, from key values to all of the keys that have that same value. So for example, my BST, each node in the BST would be correspond to some particular value, say $2,000, and inside that node I could store a list of all the transactions that have that priority, but it's awkward. Okay, so we're actually going to talk about another data structure that will avoid that awkwardness and this annoying nature. Maybe let's talk about, well, we had that new cool idea of a hash table, right? That was really fast. I seem to remember it was constant time or something, right? So you have a hash table, you add to the priority queue, and now it's in the hash table. I guess adding is 1. But then how do I get the smallest item of a hash table? Well, a hash table has no order at all, right? Like things end up in some random place. That's kind of what a hash table does. It takes data, it smears them into a bajillion bits, and it puts them somewhere random. So if you wanted to find the smallest item, it's going to be n time. Likewise, remove is going to be n time. So hash tables, as it happens, are horrible, horrible priority queues. And so what we're going to do last is we're going to talk about the so-called heap. And that's going to be a new data structure. Okay. Oh, actually, maybe I'll make a note here. Hash table, no good. Items go into random places. So it's pretty much the absolute worst thing you could do to yourself is throw them into a random place. Can't find them easily. So this heap, sorry, interrupting my stream of consciousness here. Heap will be our new, cooler, better way to do a priority queue.